prove the equation for momentum, we first need to consider the two things that we know. We know that momentum is equal to the mass times the velocity, and we also know Newton's second law, which tells us that force equals mass times acceleration. So if we consider the second law, F equals ma, acceleration is delta v over delta t from the equations of motion. So we could replace this as F equals mass times v final minus v initial, which is our delta v, over, and I'll just write delta t for now because it's not really important, the change in time. So that's just Newton's second law in terms of a velocity instead of the acceleration. But if we expand out, that's equal to mass times velocity final minus mass times velocity initial all over delta t. And here we've got mass times velocity, but mass times velocity is momentum. So therefore this is equivalent to momentum final minus momentum initial over the change in time. And anytime we've got a final minus initial, that's what we call delta. So this is therefore is just equal to delta p over delta t. And that's equal to the force. So therefore we get this expression that the force an object experiences or delivers is equal to the change in momentum divided by the change in time. So how much its momentum changes and how long it takes to do it. And this is related to the impulse. I have a very small impulse time, so I change the same amount of momentum but in a very, very quick time, the force gets bigger. So this is why if you're in a vehicle, it's much better to take a long time to stop because your change in momentum is always going to be the same. You're going to be moving and you're going to end up stationary. You want to do that in the largest amount of time because the larger the time, the smaller the force. If you hit the brick wall and stop in 1 second, the force is going to be massive. If it takes you 3-4 seconds to stop, the force gets really small. So this is the importance of the momentum equation.